So now we're going to talk about how to decode instructions. So we've talked a lot about how you build the data path, that is how data gets moved around in the processor and what goes where and what control signals we have, but now we're going to talk about how do you figure out the control signals from the instruction, or how do we decode the instruction. So here's an instruction, we've looked at this before. It's an add instruction, an R-type instruction, so it specifies 3 register values, and you can see the parts of the instruction. It has an opcode, 3 registers, a shift amount, and a function description. And let's get an idea for how these are used to figure out how to control the processor. So here's the part of the processor where we load the PC and the instruction. And we see is once we've loaded the instruction from memory, we have our instruction data here. And we're now going to use this instruction data to figure out what to do. Some of this is pretty straightforward. For the registers, we can see that we have right here the bit fields for the registers 1, 2, and the write register. So those bits can go directly to the register file. But then we need to do things like figure out which ALU operation to do. And to do that, we need the opcode and the function. So this other data from the instruction is going to go around to control logic. And the control logic is a big piece of combinational logic which looks at the instruction and figures out how to control all those muxes and inputs that we have in our processor. So you're going to get to design part of this for Lab 3. So what does the control logic do? Well, remember, here's our processor. All those blue signals are control signals, and the control logic is going to have to generate them. So register write, ALU source, mem read, mem to register, all of these signals come from decoding the instruction and figuring out which signals are needed for which type of instruction. So how do we decode different types of instructions? So that was how you would encode an R-type instruction. How about an I-type instruction? So in an I-type instruction, we have an immediate value in bits 15 through 0. So these bits in the instruction are an immediate value. They're not register values. So when we go to decode an immediate instruction, these values go directly to the sign extension. And here's a question. What happens to the immediate value for non-I-type instructions? So what goes into the sign extender there if we have an R-type instruction which doesn't have an immediate field? So for non-immediate instructions, is the immediate value not sign extended? Is it garbage but not used? Or does it not exist? So the answer is it's garbage but we don't use it. That is, we always take these last 16 bits and we always sign extend them. But if the control logic says it's not an I-type instruction, we're not going to use those values. We only use those values if it's an I-type instruction. So now let's talk about decoding instructions, all these control signals that we saw in the picture here. So we have the reg write signal, and we already talked about what this means. This means should we write data into the register file. Now when do we use this? Well, we use it on any instruction that writes to the register file. So we know that all R-type instructions are going to write to the register file, and load instructions are going to write to the register file. How about the ALU source control signal? So this controls whether we use the sign extended immediate value or whether we use a second output from the register file. So we're going to use this whenever we have an I format instruction, because I format instructions use the immediate field. How about the PC source input? Well, this determines whether we do the jump or whether we take the +4 address. So we're going to use this whenever we have a taken branch. That is, we're doing a branch equals or branch not equals, and we want to actually do the branch. How about memory read? Well, obviously this tells us to read from the memory, and the only time we read from the memory is when we're doing a load. So mem read is going to be true on loads. Similarly for mem write, we only write to memory on stores, so mem write will be true for stores. And then mem to reg. This specifies whether we take the memory data or the ALU output and write it into the register file. And the only time we're going to take the memory data to write into the register file is if we're doing a load. So this will only be true for loads. And then our last field is the ALU operation. Well, the ALU operation is determined by which instruction we're doing. So if we're doing an add or a subtract, obviously it's an add or subtract, but it's a little more complicated than that. So if we're doing a branch, well, for a branch we need to do a subtract to compare two registers. Or if we're doing a memory load, we need to do an add in order to calculate the address. So it's a little more complicated than just the ALU instruction directly. Let's take a look at two examples here. So here's decoding an R format instruction. So for an R format instruction, reg write is going to be 1. And the reason for that is because we are going to write into the register file. ALU source is going to be 0, and that's because we don't use the immediate value. We're going to take the second input directly from the register file. PC source is going to be 0, and the reason for that is we're not doing a branch. We're going to go to the next instruction, so just +4. Mem read is 0, we're not reading from memory, and mem write is 0, we're not writing to memory. Mem to reg is going to select the ALU output because we're using the result of the ALU to write back. And the ALU operation, well, it depends on what we're doing. If we're doing an add instruction, it'll be add. If we're doing and, it will be and. Now let's look at a load instruction. So for a load instruction, reg write is going to be 1 because we're writing data into the register file from the load. ALU source, well, this is going to be 1 because for a load, we're going to take the immediate and add it as part of the address. So we're going to take the immediate into the ALU. So the PC source, well, we're not doing a branch, so we're not going to do a jump here. So we're just going to do the +4 PC. Mem read, well, we're doing a load. We're going to load data from memory, so yeah, we're going to do a read. This is going to be a 1. Mem write is going to be 0. We're not writing to memory. So mem to reg, well, we're going to take data from the memory file, take data from the data memory and write it into the register file. So this will be 1, so that we can write in the data. And then the ALU operation is going to be an add. And it's going to be an add because we're adding these two values, one from the register file, one from the immediate, to calculate the address. So how do we build all this logic we were just talking about? Well, it's just like we discussed in the lecture on logic. You put together a big truth table for each control signal, and you use a Carnot map to figure out the logic function, and then you just build the logic function. You're going to get to do some of this for a simplified version in Lab 3, so you'll get some experience with it. So let's summarize what we've talked about now. So we've talked about 3 basic parts of instruction processing. How we fetch the instruction, that is we get the next instruction we're going to use. We do an ALU operation, that is doing the work, and we may do a memory access for loading and storing the data. We've talked about how most instructions do similar operations in each step. We can reuse a lot of the logic, and we can do the same things for most of them. So this makes it easier to design the circuits. We just need to hook them up in different places with the muxes and make sure we send the right results to the right place for the right instructions. We talked about how to decode the instructions to determine what to do, and we mentioned instruction bits may have multiple meanings. So the immediate field uses the bottom 16 bits of the instruction and has different meaning if it's an R instruction or an I instruction. And finally, we talked about the speed of the processor. We talked about how the slowest path through the processor limits the speed because if the clock goes faster, the data won't get to its destination on time.